Up until now we've just considered our glider to be in unaccelerated steady glides. What we're now going to look at is an accelerated part of the flight envelope, which is known as turning flight. Now, how do we turn an aircraft, and what do we mean by a level turn? Now we're going to talk about level turning flight, and a level turn is one in which the curved flight path is in a horizontal plane parallel with the ground and altitude remains constant. We're slightly different than that in a glider because we can't have a perfectly horizontal turn, and we always descend ever so slightly in a turn, but we try and minimize the amount that we descend in the turn. Now, what aspects of an aircraft affect the turn rate and the turn radius, and how do we turn? Well, the way we turn our aircraft is we bank the aircraft, and as we bank the aircraft we tilt the lift vector such that part of our lift vector creates a force towards the center of the turn. And in this diagram here, that's the red vector marked with F. The larger the magnitude of this force, then the tighter and the faster the turn will be. And as I said, we create this force in the direction of the turn by tilting the aircraft. Now the problem I have is that I'm still trying to balance my lift and my weight. And the problem's happening now is that as I've banked the aircraft, my lift no longer equals my weight, because some of my lift is pointing into the turn. And therefore, once I've banked the aircraft and commenced the turn, I need to increase the angle of attack to generate more lift, such that now my lift still equals my weight. So in order to turn the aircraft, I bank the aircraft and gently pull back on the stick to increase the amount of lift. Now, the greater the bank angle, then the greater the force into the center of the turn will be, and the faster we'll turn. But also, the greater the bank angle, the more lift we need to generate in order to counter the weight, and therefore the more I need to pull back on the stick and increase the angle of attack. Now, what I said in the start of this was that we're going to be considering turning flight, and turning is an accelerating part of the flight envelope. Now, our speed isn't changing, but our direction is. And velocity is a vector quantity, and it has magnitude as well as direction. So because the velocity is changing direction, we are therefore accelerating. And we feel this acceleration in terms of a g-force. And the g-force that we pull in a turn is proportional to the bank angle and the turn rate. And we can see that on a little plot if we can do them sums. And we see that if we've got 0 bank angle, we're in 1g straight and level flight. If I'm turning with a 60-degree bank angle, then in order to maintain horizontal flight, I would need to pull 2g. To turn with a bank angle of 71 degrees, I would need to pull 3g. And what we see here is that as we increase our bank angle, the g goes up very quickly, exponentially, as we go to higher and higher bank angles. And what we see is to go from 1 to 2g is 60 degrees bank angle, but to go from 2 to 3g is only 11 degrees increase in the bank angle, and from 3 to 4g, 5 degrees increase in the bank angle. 4 to 5g, 2 degrees. And once we get up to 6, 7 and 8g, all we need to do is increase the bank angle by only 1 degree. There are two problems with pulling g. One of them is, well, can the pilot stand it? We're not too bad in gliders because we're lying down, so we tend to be able to pull higher g than if we're sitting upright. But more importantly, if we're pulling g, the aircraft's weight is effectively increased. And what we know is that the stall speed of our aircraft is dependent on the weight of the aircraft. And therefore, as we increase our bank angle, increase our turn rate, and increase the g we're pulling in the turn, our effective weight of the aircraft is increasing, and therefore our stall speed is increasing. And we can see that when we calculate the stall speed for the various different bank angles. Now, for an ASK-21, the stall speed in 1g straight level flight is about 38 knots. If we're in a 60-degree bank turn, we're pulling 2g and our stall speed has gone up to 54 knots. If we're in a 71-degree bank turn, we've only increased the bank angle by 11 degrees, we've now gone up to 3G, and our stall speed has gone up to 66 knots. And once we get up to very high G loadings, 5 or 6, increasing bank angles by only 1 or 2 degrees, our stall speed is now up at around about 85 to 90 knots. So one thing we have to be very careful of is that when we're in a bank turn and we're pulling G, we have to be very aware that our stall speed is not constant, and that our aircraft will stall at any speed depending on the load factor or G that we are pulling.